Hello everybody. So we are back again. As I told you that in the last class what we did, we are dealing with the small angle collision frequency and we have got some insights about the frequency scenario inside plasma, and we have seen that the large angle collision frequency is small and small angle collision frequency is bit higher, but only order of magnitude. So with that we stopped and we promised that in the next class we will be dealing with the ambipolar diffusion or diffusion inside plasma. So what is this ambipolar diffusion? This is very, that amphibian, ambi, whenever we are getting this kind of thing, we believe that something which is equally applicable to both kind of species. Like in plasma, you have positive species, the ions, and negative species, the electrons. They are very common. Now, when they diffuse in the same direction equally, then the term appears the ambipolar diffusion. So, in this class, we will try to understand what is ambipolar diffusion in plasma and how it arises, what is the expression for ambipolar diffusion, and what are the insights about this diffusion mechanism inside the plasma, what species controls the diffusion, whether these are electrons or these are ions, how does it depend on the temperatures and all these things. So we start with, that inside plasma there are ions and electrons. Now, whenever suppose one electrons are highly mobile, as you know, they are smaller mass, they are having smaller mass and they are having high mobility, so they try to move away very easily. Now, the moment they try to move away from an ion, what it does actually, it comes under the influence of this Coulomb force. So this is something like they are bound using a chain, but this chain is invisible. The chain is actually the Coulomb force between these two particles. So even though an electron may try to move, ions will not allow it to move. It will try to hold it and it will say that take me along with you. So this is a motion, when diffusion occurs. When there is a gradient in the species, diffusion will occur. And if there is an electron gradient, then electron will try to move as per the gradient, but ions will say that take us along with you. So that is how the ambipolar diffusion comes into the picture. So you are clear that there may have ion fluxes as well as there may be electron fluxes. The electrons being lighter, they have higher thermal velocities and tend to leave the plasma, leaving the positive space charge behind. An electric field E is created there, and you know that how electric fields affects the flux. You know that electric field actually acts in direction opposite to positive and negative charges. If it attracts the positive charges, then it will repel the negative charges, for a fixed direction of electric field. So one is accelerated and one is decelerated. So in an ambipolar diffusion, you can understand that when the electrons are trying to move away faster, ions are not allowing them. So if at all they have to move, obeying the diffusion theory, then they have to take along with it the ions. So ultimately, the electric field will be adjusted in a manner that the ion flux and the electron flux are equal. And if such things happen, then your charge neutrality is easily maintained, as we can understand easily. So what is the your flux of ions and electrons inside a plasma. We know from our elementary classes that we can write for the ions the flux as mu I n into E. This is because of the electric field and mobility of the ions minus di of grad n. So this is the gradient in the density, and di is the diffusion coefficient. So the ions will respond like this because of the electric field and because of the gradient in the species. So this is the ion flux. Now, as we told you that ultimately what will happen, this ion flux and electron flux will be equal. Now, you know that what is mobility? Mobility is velocity per unit field strength, right? So that is how it appears like this here. And for the electrons, the flux will be minus mu e n e. Why it is so? Because the same field acts in a direction opposite to the direction that it acts for ions. So this negative sign is for that. And then this is the diffusion. It depends only on the gradient, and this is the diffusion coefficient for the electrons. So as we are now aware that these two fluxes, this gamma I, the flux of the ions, and gamma E, the flux of the electrons, these two will be equal. So we equate this. So E equal to minus, if we equate this like mu I n E minus di grad n equal to minus mu e n into E minus de grad n. If we equate these two, then you know this E and E, this can be taken out, and this is di grad n and this is de grad n. So both are having grad n. So di minus d. So this should be inside bracket for clarity, but I have taken it out. So grad n by n term is outside, and this n is coming from this thing. See, you can see n is common and E also comes out. And then mu I plus mu is there. This, if you take this to this on the left side, then becomes positive. So it is mu I plus mu e n into E. So this mu I plus mu e comes at the denominator, and di minus d goes to the numerator, and you get one coefficient grad n by n. So this is the electric field that will be created when these two fluxes, that is the flux of the ions and flux of the electrons, they are equal. From this relation, you are getting a value of electric field E, which is possible when such flux equilibration occurs. So now what you do actually, you take any of this equation, either gamma I is equal to mu I in E minus di grad n, or you can take gamma I is equal to minus mu n E minus d grad n. Any of this you take, and you just put the value of this E over there. Then what you will see that this E you have put over here, and you can then find the value of gamma E equal to gamma I equal to gamma. So this gamma is equal to the gamma E equal to gamma I. So here from you will get the value of this gamma equal to mu I di minus d by mu I plus mu e grad n minus di grad n. So if you just exchange this one, so what I have done, I have put the value of E in this expression, this ion expression, and mu I is there, then your E grad n by n is coming over here because of that E, and this n and n getting cancelled, so only grad n is over there, and then di minus d mu I plus mu e as it is coming over here, you just put over here. So n and this n cancels, grad n remains here, and then di minus d divided by mu I plus mu e is here, and then minus di grad n as it is coming here. So you just make the algebraic simplification, and you reach here that it is mu I d plus mu dy by mu I plus mu gradient. This is a very symmetric kind of expression, and you get the coefficient as the diffusion coefficient. So as I explained you earlier that this is a diffusion where both the polarity of charged particles in a plasma diffuse in the same way. So what you are getting, the expression for ambipolar diffusion coefficient as this one. This we just equate with this one. Then you are getting, this is that mu I d plus mu dy by mu I plus mu. So this is the your ambipolar diffusion coefficient. Now, what is the ambipolar diffusion equation then? You know that del n del t is equal to minus divergence of this dA gradient, right? So if you put that thing, then it becomes dA del square n. Now this is the ambipolar diffusion equation. Now, when a plasma is there, we would like to know that how the particle distribution is there inside the plasma, which is governed by this kind of diffusion equations. So what we are essentially interested to solve this equation. So here it is, see del n del t equal to dA del square n. Now you know that this n is having a spatial component as well as a time component because it is varying with time. So it is nRT, we can separate it out in separation of variable method, that t of time and s of position. So these are two functions, and then if we substitute that in this diffusion equation, then we can using the separation of variable method, and we can get an equation of this type: 1 by t del tau by del t equal to minus d by s del square s equal to 1 by tau. We can equate it with that. So if we take the time component, then we are getting a solution of t equal to t0 exponential minus t by tau, where tau is the diffusion time, and for the spatial component actually we are getting a solution of this type. Now you know that the density is 0 at the boundaries of the plasma system. That is quite natural because it is touching the wall there, and then we can reject the sign solution because you see this one here. So it should be maximum at the center, and at the edges it will be 0 actually. So what you finally get, a complete solution of the form n equal to n0 exponential t by tau. This is nothing but this one, this is exponential minus t by tau. We have observed all the coefficients in this n0, and we have put the boundary condition to get the value of this constant, and that is coming to be as n0. And you know that at t equal to 0 this part will be 1, and then at x equal to 0 this part is also 1. Then we are expecting that it will be n equal to n0, and then how that is getting changed with time as well as space, this expression is giving you there. Actually I solve this in my computer and I get a solution of this kind. Say t equal to 0, if this is the distribution, this is the n0 value, and then as the time proceeds, you see that the profile is getting flattened, flattened and flattened, okay, and these are coming in the time scale of microsecond. So here 12 is the dimension of the plasma, you know, here this is minus 0.1 to plus 0.1, so this 12 is this much. So that is the how the plasma behaves as you leave it with time and space, okay. So the profile is some sort of cosine curves it is following, and it is dying with time, and as you after sufficient time lapse, the profile almost goes to 0, okay, the plasma get extinguished. Now, what we have the ambipolar diffusion coefficient, we would like to get some insight about the expression that we have got. We got what is the dA equal to di. If we take common this di, you just go back to the expression for, so it is mu I d plus mu v di by mu I plus mu v. Okay, so this is the ambipolar diffusion coefficient. What we are doing, you remember this, and what we are doing here, we are taking this di common. So if I take di common, so it is coming at the bottom. So you can easily find that it was mu v di plus mu I d by mu v plus mu I. This is the kind of thing. And then when we take di out, and we can write this expression very easily as 1 plus d by di into mu I by mu v divided by 1 plus mu I by mu v. Now we come back to the Einstein relation, which says that they connects between the diffusion coefficient and the mobility. So what it says that d by mu is equal to kt by e. So then what we will put that this thing, actually if we put over there, then because mu e is much greater than mu I, so then we can write this one. If I put d by mu is equal to kt by e here, then we can just express this as di into 1 plus t by ti divided by 1 plus mu I by mu v. Now you know that mu v much greater than mu v, that mu v greater than much greater than mu I, as I told you. So we can neglect this term compared to 1. So what it is giving, dA is equal to di into 1 plus t by ti. So what we are seeing that this ambipolar diffusion coefficient is basically controlled by the heavier species. You see that it is di. Okay. So for thermal plasma T of the order of Ti, you know that thermal plasma is having this criteria. So what you are getting dA of the order of this giving you 1. So 1 plus 1 becoming 2, and you are getting dA equal to 2 into di. That is the, what is the ambipolar diffusion is just double the value of the diffusion coefficient of the for the ions. So di is there, but when you are getting the ambipolar effect, it is getting doubled. But anyway, it is being controlled by the heavier species, not by the electron. So whatever way the electrons may try to move apart, it is basically the heavier species which will control the motion, not the lighter species. This is one very interesting observation about this ambipolar diffusion coefficient. Now when this is dE is much greater than di and mu v is much greater than mu I, then what we find that EA, what we had actually EA is the electric field, ambipolar electric field that is getting created. So if we go back, then we can see that E is equal to di minus d gradient, di minus d by mu I plus mu v into gradient by n. Okay. So this was our expression for electric field. Now we can write this expression, you remember this one, we can write this expression as like this, E is equal to grad Ne by Ne into d by mu v. How we can do that? Because here grad n by n was there, and this is anyway there, and what we are saying that this dE is much greater than di and mu v is much greater than mu I. So we can write this as grad Ne by Ne d by mu v only. So again, if we put the expression for Einstein relation, then d by mu is equal to kt by E. So what we are getting, ambipolar diffusion field, electric field, is equal to minus grad Ne by Ne into kt by E. So electric field is now, you can see that is completely controlled by, almost completely controlled by the lighter species, and the field created is proportional to Te, so electron temperature. So ambipolar field will be more when you are creating a plasma having larger electron temperature, but the diffusion will happen as per the width of the your ions. So this is very interesting the electric field that is caused by the ambipolar effect is basically controlled by the electrons, and it is proportional to the temperature of the electrons, but the ambipolar diffusion coefficient is controlled by the heavier species, and it is ambipolar diffusion coefficient is almost equal to twice the diffusion coefficient for the ions when ambipolar effect is concerned. So this is the thing. But when we are considering multi-species diffusion, in a plasma is a very complex system, and there may be many species inside a plasma simultaneously. And in real life, we need to handle all those things in a very precise manner. I have just given one example here, that some species, the black one, is getting diffused into the other species like 3, 4, 5 and 6, 2, 3, 4, 5, 6. So there are the different other species within which this black species, the species 1, is getting diffused. So the net molar diffusion flux in this case, you have to consider like this. So what you are seeing that D12, D13, D14. So D14 gives that the species 1 is getting diffused into the species 4. So all these things you have to take into account, and you can write the multi-species diffusion flux like this one. So in actual case, you have to consider all these things, and I'll get into a bit deeper just to give you an idea of how a real system is tackled. I'll not go into detailed derivation of all those things. I'll just tell you what the different diffusion coefficients we need to handle in a plasma. Like when I am saying this 2D thermal plasma, this is not correct actually. The 2D is already telling that it is not non-thermal. So there will be electron temperature, there will be heavy species temperature. But sometimes, thermal plasma, like the arc plasma, it is mostly thermal in the core, but when you go to the periphery, the electron temperature remains high, but the ions temperature get quite low actually. At the wall, that ion temperature is almost equal to the wall temperature, which is very close to the room temperature because of intense cooling, but there the electron temperatures remain several electron volt. So that is quite high. So this type of plasma are sometimes it is 2D thermal plasma terms are given there, but to the moment you are saying 2D, you are saying that there are two different temperatures. So for electrons, one, and for the other is for the ions. So when electron temperature, ion temperature is different, you can never say that a thermal plasma. But still, this is a field of thermal plasma because in the core of the plasma, this kind of things are happening actually. The thermalization of the electrons and ions because of collision that is happening inside the core. But when you are going away from the core towards the wall, there the electron temperature remains high, pretty high actually, but the ions becomes very cold. So that is the case where in general you treat the plasma as a 2D plasma, but the thermalization case is a special case of 2D where T is same as Ti. So this is a general treatment methodology for the thermal plasma. Start with a 2T model, and wherever they are becoming equal, these two temperatures are same temperature, then that is the thermal zone. When they are not equal, they are the non-thermal zone. So in general, you have to treat that as a non-thermal plasma. Like here, it is a 2 temperature plasma. One is for heavy species and one is for electrons. So here I will go into details in the fluid simulation part. I will discuss on that detail. But here only to give you the idea about what are the different diffusion coefficients that may appear inside a plasma are like this actually. And if you are interested more in this thing, then the book by Hisfelder and some elementary, I will not say elementary, they are very basic and they are very insightful works by Devoto. He has contributed immensely around 1960 to 1980 time zone, and his works are immensely used by the community for modeling purpose. So, if you are more interested, you can go to the book by his builder, Curtis and Bird, and these publications by Devoto to get more into this diffusion coefficients. I'll just mention what are the different diffusion coefficients that appear in the plasma. So, what you are seeing here, this is a binary diffusion coefficient. Then there is general ambipolar diffusion coefficient. The expressions I have given you. This omega ij is the collision integrals. And then what you are getting, this general diffusion coefficient, this is defined like this in terms of this binary diffusion coefficient. You see that this is the binary diffusion coefficients, then you get this cofactors here, and then you define the general diffusion coefficient in terms of this binary diffusion coefficients like this. Then once you know the binary diffusion general diffusion coefficients, then you can get the general ambipolar diffusion coefficients like this. You have seen the expression that are involved here. So this is the general ambipolar diffusion coefficients. Now there is thermal diffusion coefficient. So thermal diffusion coefficients for electrons, and that for the ions are different. Okay, so not only ions, their heavy species are also accounted as the other species. So in fact, in two temperature model, you consider electrons as one species and the rest of the heavy species like ions or molecules or neutrals or double ions, all of them as another species. So that is why there are two temperature. Electron temperature is one, that is pretty high, and the ion temperatures are same for all of them, like ions, neutrals, double ions, molecules. See if they are present there. So that is how their diffusion coefficients are defined differently. This is for the electrons and this is for the ions. So this Qij, they are the elements basically. They can be expressed in terms of the collision integrals. So to know exactly what are the expression of these entities in terms of the collision integrals, then you can go into the books of this. Not this is a book, actually these are publication by Devoto, and you can get the expressions for Q in terms of the collision integrals over there. Then there comes this thermal ambipolar diffusion coefficients. So this thermal ambipolar diffusion coefficient is defined like this in terms of this thermal diffusion coefficients, and when you get this alpha like this one, this is a your general diffusion coefficients. These two come together and you get the thermal ambipolar diffusion coefficients like this over here. Then there is this finally you have to include all these diffusion coefficients properly in the transport equations to get the actual behavior of the plasma, okay, through simulation. So this looks to be complex, but if you do this simulation in a very methodical way, these are not very difficult tasks nowadays, and there are now commercial softwares. In our days, we have written all these codes in our hand, and also how they give the real-time pictures of the behavior of plasma in the later class, sometimes as it becomes appropriate. So this is this much about the diffusion coefficients. In the next class, we will be going for this plasma kinetics. So whatever so far we have learned, actually what is plasma, how plasma parameters can be defined, like your collision frequency, then there are large angle, small angle collision frequency, plasma oscillations, then device screening, and then diffusion you have learned, collisions scenario you have seen. Now, what we want to know further into the kinetics of the plasma particles inside the device. So that is very much important to understand whatever device we make, whether it is thermal or non-thermal, and how the plasma will behave against diagnosis or against the process. So we need to know the plasma kinetics. There are three theories: orbit theory, kinetic theory, and fluid model, and we'll get into all of this. The essential things we'll be knowing, not very details, but that will be, whatever we'll be learning will be mostly sufficient to handle the devices that will come across. So in the next class we'll be going for this orbit theory. Okay, thank you.